Hey everybody, I'm here for day 11 of Advent of Code. Just wanted to go over my solution and how I got there. Again, this one ended up being if you've done puzzles before, you probably know about the Manhattan distance or taxi cab problem, and that can kind of help you solve it. A naive solution. Well, let's talk about the problem and then we can go further. But the gist of it is you're given this graph right here, and you want to calculate the differences between each star. These are the stars and are the galaxies in like a map of the sky. And so the idea is to calculate the distance from here to here. You go down, down, here, 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 or some iterations of over, down, over, down, like that. Like you can't go diagonal, you can only go up, down, left, right to get there. So you might think a naive solution is is this just a graph traversal problem? Can I find the shortest distance from here to here? Or you can do that, but there's actually this is a just because I've done puzzles before. There's this notion called or there's this algorithm called the Manhattan distance, or they call it Manhattan geometry. Apparently, it's now called taxicab geometry. I must have learned this a while ago. They're both the same thing, though. The idea is imagine you're in a bunch of grid squares. How do you calculate the distance from point A to point B where you can only go right? If you're in like Manhattan or some other city that's in a grid pattern, you have to go up, down, left, right. You can't just drive as the bird would fly across the thing, right? So if you want to get from here to here, you have to go up, into the left. And if you want to go down here, you go down two, right? Here's more complex things. The notion of like, oh, if I want to go from here to here, I have to go down, down, right, right, or down, right, right down, right down, right, down, down. Any of those are the same, but it turns out for R2 space, which is just two-dimensional, which our map is, the way you calculate it is this equation right here. It's the absolute value of the difference of the x's plus the absolute value of the difference of the y's, meaning what is the distance in one direction and what is the distance in the other direction, and then you add those two up, and that's how you that's how you get the Manhattan solution to it. So that's what this problem is at like a really high level. Is do you know what the Manhattan problem is? And if you do, this is relatively easy to figure out, because you can just say, oh, the Manhattan problem from here to here is, that calculation, which I'll show you how you do that in code in just a second. The one additional thing, though, is they tell you, hey, there's something that you should also know. In any row or column that contains no galaxies, meaning there's no hash in any of those rows are actually counted twice instead of once, right? So if you see here, in the original example, this row 3 has none, so it should be counted twice, right? So when you're going from here to here, you're actually going 1, 2, 3, 4, 5, but you crossed over this zone right here, which is actually 2. So as opposed to the answer being 5, it would be 6. And in the way that they describe it, they say, oh, you should expand the universe first. That's probably that's not the way I ended up doing it, but if you expand the universe, it would look like this, where you say like, oh, now I'm going to add a row here, and so now it looks like this. So when you do the calculations, you can go 1, 2, 3, 4, 5, 6, right? And then so the solution to the problem is you want to calculate the distance from every star to every other star and add them up, right? And so the rest of it is showing you kind of how you do that. Is like if you have 9 galaxies, you'd want to know the distance between this one and this one, this one and this one, so on and so forth. And then from this one, you'd want to know the distance from this one to this one, or this one to this one, this one to this one, this one to this one, and so on and so forth. You it says only count each pair once, right? So that's basically just saying if you're calculating the 6, if you've already calculated 1 6, you don't have to recalculate 6 1 again. You already know that distance. You've already added that to your sum, so you don't have to do it a second time. So again, how do you solve that? Well, your initial inclination may be, okay, I just expand the galaxy and then do the Manhattan distance. That would potentially work for part 1. It would be much harder for part 2, which we'll talk about in a second. But if you happen to know the Manhattan distance, you may shortcut it and say, hey, I know what the Manhattan distance is. If I can just see how many times we hit a row or a column that has an empty space, I can just add to that item, right? So as opposed to doing the actual expansion, if I know that this row 3 is empty, anytime I'm calculating the difference or calculating the Manhattan distance here, I can just add an additional one because I know I crossed over it. And you just do that for every row or column that you would go across. So I hope that makes sense. Again, I tried to explain it really quick, kind of like in my thinking process how I solve that. So how do I solve that in real code? Well, first I get the input. I just turn it into a grid again. I think we've done this before, right? Where like for each of the lines, get each of the characters and collect them as a vector, right? So now I have like a 2D array of characters that describe each point in space. From there, I can figure out how many I can find, which of them are stars, and I created a point object, which I'll show you in a minute, that we use. But the idea is I can then create a point in the space or in the grid where each of the stars are. So it's a star if it's a hash. So basically we just enumerate and then do flat map, which I talked about last time, basically taking an array of arrays and turning it into an array. So I'm iterating over the x's, the y's, which are the rows, and the x's, which are the columns, and enumerating over them. So I get like their index value. And then I just filter each of them by, hey, is the character at that point in the grid a hash? And if it is, I can just map them to a point in that thing. So this stars value, it now has a vec of points. You can see it down below there. It's just a vec of points. So it's gone through and found all of I called it stars here, but it's actually galaxies, right? So find all the galaxies in the point. And then I was talking about the algorithm a little earlier. I need to know which rows and which columns are completely empty. And so you can do that with the all function or all method. So basically what I do is I just iterate over all of the rows in the grid, and I check to see if all of them have a dot, if all of the values in that row have a dot, and if they all do, then that's one of the empty rows. I do the same thing for columns as well, right? Except this one looks a little bit different because instead of iterating over the grid, I now have to iterate over the columns, which are single values within there. And so the way that I do that is I just create a range from 0 to the end of the grid, and I filter where the element in that row's X position is a dot, where all of them are that, right? So it's the same thing as up here. It's just what I'm doing down here now is saying, oh, I need to find the columns I need to find the column values in each of the rows, as opposed to just saying I just need to iterate through all the rows. But these are essentially doing the same two things. I'm finding which rows are empty, and I'm finding which columns are empty. So I have a list of stars that I'm going to have to find the distances between. And then I'm going to have a list of rows and columns that I need to check and see if if the stars would cross through those things to solve the problem. And that's how you solve it for part one, is you do the sum distances, which is that algorithm. So what does that look like? Oh, let me point out, here's my point first before we go into that sum distances. I added a couple helper functions here. First, you can calculate the Manhattan distance between any 2 points, right? Self and other. And what does that look like? Again, it's just the difference of the x's plus the difference of the y's, their absolute value, right? Like the difference of those absolute values. I also calculated the mins and maxes, and this will become apparent in the algorithm, but when you're trying to find if 2 stars go over a row or a column, you kind of want to know the minimum x and the maximum x, so you can see if they're within that range. But I'll show you that in a second. So these two functions just return the minimum x and minimum y, or max x and max y, of the 2 points that you're given. It's yourself and the other. Okay, so how does the sum distance algorithm use all of that stuff, right? Well, we know the problem says it wants to give us we want to give it a sum of all of the distances between the galaxies. So we're going to be tracking that in our sum variable. And then we just need to iterate over each of the stars. In this case, I enumerate because I want to know what position I am in the star, because I want to calculate for the other star, you're going to check the distance between. I don't need to calculate stars that I've already calculated previously. And the way to do that is, here I'm just using a slice, right? I'm saying for the other stars, I want to start at the ith plus 1 position. And the way to think about that again is, if I'm down here at 6, I only need to calculate 7, 8, and 9. Or where is that thing? Right here. If I'm down here at 6, I only need to calculate from 6 to 7, 6 to 8, and 6 to 9. Because when I was at 1, I already did 1 to 6. When I was at 2, I already did 2 to 6. When I was at 3, I already did 3 to 6. So there's no need for 6 to calculate the values above it. And so that's essentially what these 2 for loops do, is you say, hey, iterate through each of the stars, and for each of the stars after it, we want to calculate their Manhattan distance and the number of times they traverse each row or column. So that's what this code does down right here. We say, first, let's just calculate the Manhattan distance. So how far are the two, sorry, I keep saying stars, but how far are the 2 galaxies between each other? And then what you do next is you say, I need to add any expansion values for each row or column, the Manhattan distance, like if you did it in the walking path thing, how many of them you would hit. So that's where I get the min x and min y and max x and max y right here, those point methods I talked about above. And then all I need to do is just know in the empty rows and empty columns, how many of them are there that are in between those 2 stars, right? And so I do that with a filter function or filter method. I say, for the rows, I want to filter by any row where the min y is less and the max y is greater. This is just essentially, you can think about this as saying, if I've got 2 stars here, I only want to consider the rows, that are between them, that are in between them, right? Find all of the empty ones that are in between these 2 values. If there's one outside of it, I'm not interested in that one because I'm not going to use it to traverse to the star. But so I'm just going to find however many of those are rows, and I'm going to do the same thing for the columns, right? So in the columns, I'm going to have these 2 galaxies that I'm calculating the distance, and I know I'm going, and the ones I'm going to traverse through the empty sets happen to be the ones that are in between here, right? So if there's a column right here, I would want to include that. And that's just with this filter function, and then I count them. However many there are is how many times I would increase the distance. And so to add to our total is just the distance plus the number of rows that I would traverse plus the number of columns that I would traverse that are in my empty rows and columns. And that's it for part one. It wasn't too hard. Again, most of it was the fact that I've done Manhattan distance problems before. And so when I was reading the problem, I'm like, oh, this is clearly a Manhattan distance problem. Just the gotcha was, or not the gotcha, but like the special case was, well, now what happens if I have this expanding universe issue where some of the distances are now larger than they were before? So if I run it, you can see here's my answer to my input. It's some very large value because, again, the map is much bigger than the test cases, right? The actual grid. So how does it differ in part two? Well, all it really says is, hey, you know how we were talking about expanding the grid? Instead of expanding it one time, we're actually going to expand it 1,000,000 times. And this is where if you had actually said, oh, I'm just going to do like a find a path function, your algorithm would now be substantially much more difficult, right? As opposed to 140 by 140 and increasing those rows and columns by maybe like, I don't know, 100. So you get like somewhere on the order of a 300 by 300. You now have like, like a 3 million by 3 million column or 3 million by 3 million column grid, which is just huge, right? And now you may struggle to do those pathfinding algorithms. If you knew about the Manhattan distance though, and already known where to go, it wouldn't have been that hard to change your code. And that's actually what ended up happening to me. Again, it's just I was looking at some Reddit stories after I solved this, and there were several people that were like, oh, I feel like I just don't understand how to solve these puzzles. I thought I was a good programmer, but maybe I'm not. You were probably a good programmer. These puzzles are a different beast than getting a feature from a business person and implementing that in an application, right? That's a whole different set of tools and knowledge and skills that you need to have to do that. Solving these problems is just from experience, right? If you've tried to calculate the Manhattan distance before, this problem fell right into your lap, right? So what do you do when you go from, oh, it expands by 1 to it expands by 1,000,000? Well, I just happened to have this, I added an expansion value to my sum distances where I said, how much do I want to expand each of the empty rows or columns? And then after I've done my count of empty rows or empty columns, I just multiply that by my expansion number. And so for part one, the expansion is 1. For part 2, the expansion is 999,000. And again, why is it 999,000 versus 1,000,000? This is one of those off by 1 things where one row becomes 1,000,000 rows. One row becomes 2 rows. And so if you think about what's happening there is you already have the first row, and the question is how many additional rows are you adding to each of those? In the first case, you're adding 1 row. In the second case, you're adding 999,999 rows. So you could have solved this another way. Is you could have said, oh, the expansion is 0 and the expansion is 1,000,000 here, and then you just did some a subtraction down here. Either way would work, but the way to think about how you expand is you say, oh, I'm adding 999,999,999 rows to each empty row or each empty column. So that's it. That's part 1 or 2. Just to reiterate, the idea is if you know the Manhattan distance, you just calculate that distance, and then you just need to find the rows and columns that need to be expanded between those 2 points. And once you've done that, you can add that to your Manhattan distance. Part 2 just changes the expansion quantity. Instead of it being 1 is 1,000,000 minus 1. Anyway, so I like the problem. If you're a puzzler, this one wasn't very hard to solve. If you're going back to your CS days and you think, oh, I could implement this as a graph and do a graph traversal thing to try and find the shortest path, you would have probably struggled a little bit, especially on part 2. I think you could have definitely done part 1 this way, is if you just say, oh, I'm going to take the graph, I'm going to expand it, and then I'm going to do some kind of shortest path function. You probably still would have been able to solve it okay for part 1. It would have been harder in part 2 just because the size gets bigger. But again, that's just the way these puzzles are. So it was a fun puzzle for me. I'd love to see how you guys solved it. Any other ideas? Also, I'd love to see if you have any thoughts on improving my code. I noticed that a lot of my code was using itters here. Sometimes that's really cool, and it means like if you're translating it to another language like Haskell or whatever, it probably is not hard to translate this because I'm using a lot of like Haskell-y type things or functional type things in here. But again, I would really love to see how you guys solved it. I had a lot of fun solving it. I just happen to know this one. I promise, I know I've said this every day, but eventually we're going to get to a point where I just won't know the answer, and I will have spent a lot of time researching it, and I'll talk to you about that research process when we get there. But it just so happened reading this one, I'm familiar with the Manhattan distance, and so solving it this way wasn't too tough. Just with that extra gotcha at the end. So again, I really appreciate everyone watching the videos, your comments and stuff. Thank you very much. And I hope you guys and gals have an awesome day.